How do you build a strong structure that can accommodate stress without it becoming dangerously heavy or too expensive to produce? Well, 100 years ago, the designers of the Williamsburg Bridge in New York opted for a lattice structure with metal rods connecting at nodal points. It's fair to say their design has lasted well, but this wasn't down to dumb luck. Their approach was founded on some very sound principles. And these same principles used to build bridges 100 years ago can be applied today in the design and manufacture of nano-lattice materials, lattice structures with nanoscale constituents. Let me tell you some more. This is ASU. If I give you a stick and I ask you to break it, chances are you're going to bend it and snap it into two. You're not going to try and stretch the stick till it breaks. But why is it easier to bend and break than stretch and break? It boils down to how stresses develop in the stick when you apply these different forces to them. And the stresses from bending are higher than those from stretching for the same amount of load. You can use these concepts of bending and stretching to design lattices that can be used for a wide range of applications like lightweighting and energy absorption. This story starts in the 1800s during a period of expanding construction and growth in infrastructure. And one of the important needs at the time was developing theories for how to design structures like bridges and roof trusses that could survive the loads being placed on them. James Clerk Maxwell, yes, that Maxwell of electromagnetics fame, published a paper in 1864 which discussed the stability of rigid truss-like structures, which was useful in answering questions like, how many truss rods do I really need in a bridge? Maxwell proposed a way to formulate what were the just right number of rods in a truss structure. Too few, and the structure will deform excessively under load. Too many, and the rods in the structure introduce unnecessary stresses in themselves. This idea is captured in what is known as Maxwell's stability criterion, and it involves the computation of a metric M with B struts and J joints as follows. In two-dimensional structures, M is equal to B minus 2J plus 3, and in three-dimensional structures, M is equal to B minus 3J plus 6. Per Maxwell's criterion, and assuming the joints are locked, three scenarios are possible. If M is less than 0, the structure is under-constrained. We have too few rods for a stiff structure. If M is equal to 0, the structure is a rigid framework. This is just right. If M is greater than 0, the structure is over-constrained, and this results in internal stresses and unnecessary mass. Nearly 150 years later, as additive manufacturing, or 3D printing, made it possible to now fabricate truss-like structures in 3D printed parts, designers started borrowing ideas from atomic arrangements in metal crystals. In material science, we call the way in which atoms are arranged in a crystal a lattice. And hence, when it came time to creating three-dimensional truss-like structures, we borrowed the term. And since truss rods conjures images of large bridges and rooftops, we use the word strut instead. The question material scientists and designers were asking now was, however, similar to the one civil engineers were asking in the 1800s. How many lattice struts do I really need? And the ideal number for a stiff lattice is one that gives an M value of 0. These are lattices that transfer loads axially, and we call these stretch-dominated lattices. However, not all lattices need to be stiff. In some applications like the sole of your shoe or the cushioning foam in a bicycle helmet, we would like the lattice to deform and absorb energy. For these applications, we can choose a lattice design that gives us an M value less than 0. It is under-constrained, and the individual struts deform by bending. This is what we call a bending-dominated design. There are, of course, many different ways of designing lattices, and many applications, some of which may even not be structural in nature, where knowing if the lattice is stretching or bending dominated is useful. Today, we design lattices using powerful computational design tools. We select a particular lattice based on its performance in simulation or in experiments, or even because it evolved in nature for a particular function that is of interest to us. But every now and then, we whip out Maxwell's criterion and check how many struts and joints there are and predict if the lattice will be stiff or compliant under the application of loads. The application of these kinds of lattices are endless. They give strength with low density, and that's a combination that has real power. From biomedical implants to jet engines, insulation, and building structures, this body of research has real-world application. Starting with Maxwell and going via those designers of the Williamsburg Bridge, we know that with the right structure designed for a specific use, we can develop incredible strength and versatility in just the ways we need it. This was ASU. Thanks for watching.